stop sharing your screen, please. So the next talk is by Caetano Rodrigues Miranda. Can you make it full screen, Caetano? Yeah. Okay, so this is Caetano Rodrigues Miranda from the University of Sao Paulo in Brazil. And he will talk about materials discovery for biomedical applications, from machine learning and first principles calculations to finite elements.
Thank you very much, Shabana, for your kind introduction. I hope that is everyone well, and I actually would like to be in my beloved Trieste to have a narrow in the ICTP cafeteria. So I'd like to thank the organizers for this incredible opportunity to give this talk in the Total Energy online. And it's very interesting to share this work that has been a combination of expertises like the materials engineering, the chemistry, mechanical engineering, and a physicist towards the proof of concept to use materials discovery for biomedical applications. Now, the seminar is actually all about the use of a combination of multi-physics and a multi-scale approach. We're going to try to figure out biomedical applications where you're going to use machine learning together with first principle calculations in order to check and verify the properties of the systems, and basically try to end the cycle to look for real applications. So you're going to see how this elastic properties is really works on a bone, for instance. Now, the motivation is looking for the structural biomaterials and bioimplants. You are very much interested in that because of the use. So you have this interface between the bone and the implant, and this requires several the right combination of the density as well the elastic properties of that in order to avoid the bone stress shield effect. Now, in the case of the bone, this is very complex material. In this interface between the metallic implant with the bone, you have several challenges here. So one of them is that you have a very rigid part, the external part of the bone, but also have a low modulus region that is actually with the soft part and where you have the blood and other bioactive things happening. So what you're trying to see is how can you look for materials that have the right combination where you can use it, for instance, in bioimplants, and also to avoid fracture, and particularly you have a huge pain in case of you have this disbalance between those materials. So this has been motivated because in Brazil, this is actually a huge market. You were talking about something of the order of $4 billion a year that you lose because you are not able to have those materials or those systems to use ourselves. In this, with the population aging, is this supposed to have even more needs with this kind of systems. Now, of course, you have already several options in place. The most of them is related to titanium, metallic titanium, where the current best one is the so-called the gunmetal, where you have the TNZT alloy. Here you have a very good combination between the low elastic modulus, the good biocompatibility, high strength, but the problem is the high cost of it. So you are looking for, particularly here, materials that have low cost, but you still have a good balance between the yield strain and the moduli, particularly looking for the elastic absorbable strain respect to the cost. So this family of systems is here, and we'll try to look into something that is more at low cost, but still have the good properties from in the biocompatibility. Now, the first thing that you have to do is to look for the periodic table for the bioimplants. And basically here you have the metallic systems. This is the elements only. and looking for the biocompatibility of that, and there are several other properties that you have to look for. In this particular case, you search only for the green ones. It is for us, it will be you could avoid any problem for the biocompatibility, and then requires the titanium, zirconia, and niobium. But of course, you have the ruthenium, but the ruthenium is better to use for catalysis, and also you have a very high cost on that. Now, in this way, you are looking for alloys that have this combination, titanium, niobium, zirconia, and you hope that the elastic properties can reach those this region, in particularly low cost. But the problem is what to be the composition of that. Now, to do that, one strategy is that people use a lot on the material discovery. Now, it's still a very try and error. So, but the problem here is that you have a multi-dimensional optimization problem that you have to look for which is the best composition for a given system. However, most of the time, the parameters and the properties are unknown. So you have to look for that. And the one way is to only search for the best candidate. So in this way, you can synthesize, characterize, and test it is in the way that you can save a lot of time and also cost. So the approach that you're going to use is actually back in time in terms of the evolution of the methodologies from the scientific point of view. You're going to use machine learning methods in order to make a selection of potential candidates. Then you validate it with a dense functional theory. Then you're going to use the linear elasticity to see for real applications before doing actually the experiments on this system. Now, the methodology that you have used is a combination of multiphysics and multi-scale methodologies that you want to narrow down the possibilities in order to apply for a real system. So in this way, we start with databases. In particular, here you have used the materials project. And remember that one thing that has motivated us a lot on this work is that because in Brazil, 8% of the niobium is here, and could be something that could be used for from the economical point of view. Now, you have used machine learning methods in order to get information of the elastic properties based on composition. This was some of the packages and also libraries that you have used. With that, you select some of the materials and you test it with the dense functional theory. When here, particularly, you have a problem that you have to use the special quasi structures in order to approach the alloy problems. Now, this information that comes from this functional theory then is used to feed the elastic properties, where you perform some finite element simulations. You could see if the alloys and systems that you search is in a good shape to be used in real conditions and also for real applications. Now, how has been done this several steps under the way to reach the full alloy and the material itself. So we start with the composition structure, as has been seen in several of the talks today. So you narrow down the possibilities, looking only for the transition, post-transition metals. This gives to you this amount of entries. Now you filter out even more. You excluded any ionic or covalent character of those systems. Then you look also for elastic properties in the range of titanium alloys. That is interesting for us. And finally, the information that comes from the heat formation and the entropy mixing. So this gives to us around 2,000 entries. Now, what you are looking for is to be able to predict the elastic properties based only on composition. So using this machine learning process. So in this way, one important step is to look for, in the exploratory part of the machine learning process, is to look for which features will be potentially the best in order to describe a given target property. So to do that, you do a feature selection. So you could figure out what is the best features that can somehow let us have a model based on the only based on composition. And finally, this has been fed some linear models or random floor regressors in order to be able to train a model towards the book modulus or the shear modulus, again, using only the composition information. So this was more or less the step regarding to the machine learning process. Now, just to give you an idea about this has been done for the shear modulus. Here you have you explore several options. One is linear regression or random forest, as well the neural networks with the full descriptors and select a number of descriptors. So based on that, you could see that the database compared with the predictor in our model, in particular for the random forest, is quite interesting. And I also have a very small error compared with the other system. Now, you have been able, with this model, to apply a selective one. Here you use the Keras library in order to have this information. And then you are able to get what is the best features that somehow can capture the elastic moduli using basically using the composition. Now, in this particular case, for the shear modulus, you end up with the Poisson ratio to be the most representative one. Of course, you have other ones that I can comment later on. But somehow, with this information, then you are able to get the phase diagram, the titanium, zirconia, and niobium, using this moduli, using only the composition information to get information from the elastic point of view. So in this particular case, I'm showing the Poisson ratio that is somehow related with the mixing entropy. And you could make the correlation between what is this machine learning models is given to us together with the physics behind those systems. Now, this is very interesting. So you could do then they calculate the elastic moduli. This is what you see is the machine learning prediction using two completely different methods, the random forest and the neural networks. And we end up with a very interesting sweet spot here, on where you have a large concentration of titanium, and then you also have the combination of zirconia and niobium. So this could be seen in both methodologies, in both models. In this, with that, this was the map for us to look for those compositions in order to see if you can end up with a material with a low moduli, that elastic moduli that can be applied on bioimplants and bio applications. Now, however, I have to remind you that this machine learning predictions is only based on composition, means that it's agnostic to the structure. So this is where you have to use the first principle calculations, for instance, in order to understand and validate if those compositions are really stable, and also can be used as a good material for bioimplants and biostructures. So this is more or less what you have done. So for this under the sweet spot on this composition, then you look based on first principle calculation about the phase diagram. And here I show to you the phase diagram of titanium with pressure and temperature, because you have to look for if the structure that you are looking for is really the one that can be stable for a given situation. In this particular case, since titanium is the largest amount in alloy, you are looking for the beta phase, that is the low modulus ones, that is the BCC phase. In particular here, you have to avoid 2 points. One is the transition between the low temperature phase, the alpha to beta. And also, if you cool it slowly enough, then you can reach this region that is the one that you would like to go. And finally, if you do a fast cooling, then you may end up on the omega phase. So this is a problem.
Caetano, you have 5 minutes left.
Great. Yeah. So then you figure out here you get a phase that have a higher moduli. So you have to understand from the thermodynamic point of view, from the elastic point of view, what is going on. So then you have done a series of calculations based on this functional theory to see how is the stability of both phases, the omega and the beta, and also the beta with respect to the alpha one. Now, because of the time, let me just quickly show to you what you have end up. So you look for the influence of the zirconium, then you keep it fixed, this content. Then you change the amount of niobium, because the niobium stabilize the beta phase in titanium. So looking for this degree of collapse between the omega in the beta phase, where you have the perfect omega phase, and here will be the beta phase, and also the competition in energy between those. You could see that if you change the amount of niobium in the system, then at regions above 11%, then you stabilize this beta phase. That is the one that you would like to go. Now, you also look for the one for the competition between the beta and the alpha phases. This is you calculate the Gibbs free energy. And you see as well that you will increase the amount of niobium, then you have a higher niobium composition, goes to lower beta transition phase between the alpha and the beta phases. Now, with that, you could see that this amount of niobium will be interesting in order to stabilize the system. As well, you have to see if how is the elastic property. So this here, I'm going to show you a two-dimensional information for the elastic moduli with increasing niobium content. And in summary, what I can give more detail later, but in summary, you could get a best composition and based on the elastic property. So basically, the information is that for the contents with niobium above 11, you have a good candidates for the bone implants. You figure out the special compositions, and you calculate the full elastic properties of that. And finally, of course, you have some differences between the machine learning and the dysfunctional. This is expected, but it's still in a good shape compared with the experimental part. So this means that these compositions can be a potential for alternative for TNZT as a standard material. Now, this is very interesting because in the end you could figure out a nice composition that gives to us good elastic properties. Now, to the end, then you have applied that for implant models. So you have usually actually a bone and try to see if you have fixing a plate on this bone, how is the effect of that? As well, you have this model for the hip joint implant model, where you look at how is the response of those systems regarding to the elastic properties of the bones, as well as the alloy properties that you have figured out together with the reference one that is usually commercially nowadays. So just to give you an idea about how is the effect of that. So here's the stress distribution for the implants. So you are talking about this region of the bone, and you have this plate that fix these two parts of the bones if you have a fracture. Now, if you compare the stress response of the alloys that you figured out together with the reference one, basically you have a very similar mechanical behavior. So, and also it's well, I mean, the performance compared with the titanium alloys is much better. Now, you also, this is the example for the other model. You have a similar result. So basically, compare with the reference one, the stress, here is the von Mises stress, is more or less, you have a very similar response from the mechanical point of view. And this implant usually is put it here. Oh, and then you have this very complex combination that you have the interface between the bone and the implant. In those materials that figure out have a good response. Now, just as a concluding remarks, so the machine learning was able to capture the features, define a composition sweet spot, figure out a low modulus alloy. The ab initio calculation allow us to explore the composition rates. So here in particularly you see the importance of niobium to the structural and the electric properties. And you could get optimal ternary composition for those applications. And finally, the finite element simulations could allow us to explore real case systems, and you have a very good combination of the ternary alloys that you discover together, compare with the standard TNZT alloy that you have it done. And basically, you didn't see any significant difference between the stress response between those alloys. So, as a take message home, so this multi-scale approach allows to predict and also to propose a comparable material with the standard TNZT1. And now you are trying to see if you could synthesize those and make a real application. So with that, this has been shown on this paper. And finally, I would like to thank my team in Brazil, in particular, Daniela, Bruno, and Camilo for those, and the Brazilian funding agencies that support this work. And finally, thank you very much for ICTP for everything that has done to myself in my career. Thank you very much, Shabana. This is it. And I'm open for questions. Yeah.
Thank you, Caetano. There are actually several questions. I don't think we'll have time to take them all. Gianmarco Rignanese has a question. Gianmarco, can you ask your question?
Yes, I was wondering how you perform feature selection. And in particular, I was wondering if that's so important when you do a random forest.
So the one that you have in this particular case, you have done, you have used a set of around 550 features that it was available for those materials. And in this particular case, you have used this Keras library to make this selection. Now, regarding to the for the random forest and the other methodology that you have used, so what would you like to see here is actually how robust was this particular region that you're looking for. And in this way, you have done first with the random forest and see, I mean, the amount of the error that you have there was good enough, but you try a completely different way, that was the neural networks, and this part that was the one that was robust for us. Now, for the it was interesting to see that for the different cases, several of the properties that come out as good descriptors was more or less the same.
Okay, maybe you partially answered his question, but Nathan Daleman has a question. Can you ask it, please? Hello, are you there? Yeah.
Yes. So it's actually on the same slide. So I was wondering where the what causes these differences between the random forest and the neural network on slide 9, where you were showing the comparison. So in the region that you are interested in, they give quite similar prediction, but then outside of these regions, is this due to the feature selection or due to something else?
So we imagine that, yeah, you imagine, I mean, that this may definitely due to the feature selection that was not exactly the same that you have obtained both. However, for the particularly the general response was more or less a similar one, and you have been very much interested on this particular region here. It was the one that called us the attention, and it's supposed to be the ones that could have a better applicability for our application.
Mm-hmm.
But the fine details, yeah.
Which
okay.
Okay, yes, I'll yield the time.
Okay, we're sort of running behind. Yeah.
No, I just commented that I can write in the chat the final details about why.
Okay, we're running behind time, but maybe I'll just allow one last question. Hannah Rubin, can you ask your question, please? Hannah Ruben,
Sir,
are
I
you there?
see, I saw it. Yeah, I'm there. Can you hear me?
Yes.
Ma'am, can you hear me? Yeah.
Yes, yes.
Thank you, sir, for the nice presentation. Sir, I just want to know, in your slides that you have shown, you have calculated the role of the p valence electron, but for the transition elements, the d valence electrons play a vital role in because of their hybridization and the elastic properties. So I just want to know what is the role played by the d valence electron in this case.
So the d valence was part of it, but as you can see here, it does not come out as the really compared with the other features that remember. One thing that we are very much interested here is to have a model based on composition only for the elastic property. So even it can be an important feature for the electronic point of view, for instance, but this, in this particular case, where you're looking for the elastic properties, it does not come out as the one that is relevant compared with the other one. I don't know if
yeah.
Okay.
I think we're out of time. There are many more questions, many more raised hands. So I'm sure Caetano would be willing to answer if you were to approach him.
Definitely,
offline.
yes.
Okay, thank you for a very interesting talk. And we'll move on to the last talk in the session. This is by George Dungich.